figure out who is the next presenter. So the next talk is include only literals incorporation. And I assume that Prajwal Kumar Sahu will present his work. Online, right. This will be switched. Oh, Sven will be, yeah. All right, so it looks like Sven will be presenting. And just a quick intro to the Sven. So he is now a PhD student with the University of Agder, but he has a really rich industrial background, and he owned a company which was bought by semiconductor, if I'm not mistaken. Anyway, so very rich background, and then he decided to do some research in this area. So Sven, I hope you can hear us and let us. Hi.
Hello, thank you, Anatoly. I'm sorry for not being able to be in Newcastle due to yesterday's travel disruptions. This has been a bit back and forth whether who is going to present. I think now Prajwal is ready to present, and that's probably the best option because he has done the main part of this job, so I can join in if necessary. Prajwal, are you available?
Hello, am I audible?
Right. So Prajwal, he's a graduate from the Indian Institute of Technology, and now he's working with the University of Agder. All right, Prajwal. So if you are ready to start, you can do it now.
Yeah, can I share the slides from my side?
Yeah. What is the presentation? If you share your screen, please.
Yes, I think we need to make them a host or something.
All right, yeah. Well, we'll try to make you a host. Yeah, so we'll make you a host for the demo.
You should be able to share your screen now.
Please try to share your screen now. So you. Right. Yes. So we can see everything.
It's visible, right?
Yeah. So if you simply press F5 to start. Excellent.
I can start, right?
Yes. Yes, please.
Hello.
Yes, Prajwal. So we can hear you, so you can start, please.
Yeah. So good afternoon, everyone. This is Prajwal Kumar Sahu from Indian Institute of Technology, Bhubaneswar, and today I'm going to present the paper on enhancing inference performance through include only literal incorporation in Tsetlin machine. Yeah, so like as you know all about the basics of Tsetlin machine, like it's an learning algorithm that optimizes behavior in an interpretable and low energy consumption way, and it solves pattern recognition problems by building if then rules. Like if I have to simplify it, like if there are some conditions which are met, then it classifies it to a given class. So for MNIST data, like as an example on the board, you can see if you can say to identify number one, there may be some conditions like it should be a single straight line or single line, and there should not be any curves. Then based on these conditions, it basically finds out these conditions from the training, and then it forms a rule like if single line and no curves, then number one. So technically these rules are known as conjunctive clauses, and the conditions which are being ANDed are known as the literals. So in short, the conjunctive clause is an AND operation of some of the selected literals from an input. So this is the overall overview of the multi-class Tsetlin machine. It involves input binarization, which then goes to each of these conjunctive clauses and goes through a summation process and an argmax operator. And finally, based on the votes, you get the output. You can see also in the clause we have set these small learning units known as Tsetlin automata, which are basically some finite state machines, which go through a reward or penalty feedback kind of system to decide whether a particular literal should be included in a clause expression or not. Moving forward, let's come to the standard inference in the Tsetlin machine as we all know it. So basically, we have all the literals coming from the input, let's say in an image, or in this example, like there are two inputs, and the literals are basically the inputs along with their conjugates. So we have like two inputs and their conjugates, they form the literals. And based on the TA action, you can say like after the Tsetlin machine is trained, you either literal is included or excluded. So based on that action you get from the TAs after training, this is what the standard inference is like to form the clause expression. So as you can see, the excluded literals are basically masked out in this OR gate by driving one of the inputs to 1, and hence only the literals which reach the AND gate are the ones which are only included. So when we like wrote the expression for this, you can see that the output is basically the AND operation of a series of negation of TA action and OR with the literal. So TA action is basically 1 if the literal is included and 0 if it's excluded. And the literals output are as known. So you can see that these things give a very long expression when the number of inputs are very much. And for the size of n input, like you need to have an array of n OR gates and one n input AND gate. And it's like for very large data sets, like even for like MNIST, like the architecture like would be very large and very high resource consuming. So you can say like it's not able to scale. So one of the things which we observed and we caught on was that the trained TA models say that the actual number of included literals is just around 10 to 15% of the total literals in the model. So what I want to say is basically instead of like doing all this or masking and everything, you can directly just, if we have the literals that are included in the clause expression, you can just directly AND them and go forward. So this small example, like if there are like 3 literals, instead of like just taking negation of the TA action, like ORing it and then ANDing it, if we just have the include literals, which are literal 0 and literal 2, we can just like form an expression with just the 2 literals without going through all the steps. So in short, we actually don't need all the inputs to get our inference out of the multi-class Tsetlin machine. We just need the included ones only. This is the idea behind the include-only architecture. So, like summarizing it very short, like this is the left side diagram is what would have been given in a standard Tsetlin machine, and we are kind of trying to reduce it to the one on the right by just simplifying the architecture. But another thing is that if we had to scale it, we have to come up with a sequential solution. So to compare our results properly, we made a sequential counterpart of the inference architecture where you can just say that every clock cycle, in simple language, every clock cycle, one literal is being processed. So in the left side, as you see, instead of like these 4 literals going together to this OR and AND gate, like in first clock cycle, let's just say literal 0 goes, then 1, then 2, then 3, then it takes 4 clock cycles. But on the right side, like you can say only literal 0 and literal 3 goes, so that will take 2 clock cycles, just for an example. So like we need it, like this is just a visualization of why do you need the include only inference. So this is a matrix where the green boxes show the literals that are included as per the training, and the red one shows that they're not included. This was just like from a random clause for training of the MNIST dataset only with the parameters as shown. And hence you can see like the number of includes are very less compared to the number of excludes. So this include literals actually help in the inference process. And if you can find a way to locate this literal specifically, and put them directly in a clause expression other than going through the OR gate and masking the excluded ones. Like we can very much simplify on the memory resources as well as on the time. So our include only architecture does this pinpointing of the includes only by a multiplex addressing scheme. So like this was the methodology we used. We did some feasibility test on data sets to ensure that we can fit the complete MNIST data set in a given TM model. Then we did some tests to identify the included literals, like how much of the literals are being included for what parameters, tweaking the S and T parameters to get an optimal accuracy. Then we designed a custom inference RTL, the sequential design which I was talking about, so that every clock second one literal is processed, and due to the included only architecture, that literals is the included literals only. And then we tried to deploy it on a FPGA board, which was a Z board, I think 7000, which is a low cost development board. Yeah, so I was talking about pinpointing the included literals. So this is the addressing scheme we came along with to address them. So you can just see, like, for a given literal, the information we need to pinpoint it from all others literals are a class address, a clause address, and the literal address itself. So you are using block RAMs. These are the specialized memory units on an FPGA board to store our encoded data. And this is you can see the structure of the VRAM and how the data is arranged. One thing that we came along with interesting is that as the size of the VRAM was like subjected to only 32 bits, and we couldn't tweak around with it by making it 24 or something, there were some redundant bits at the end, because initially the aim was to fetch one literal from one image only, but then we were getting some 7 redundant spaces. So we thought, why not just like multiply the architecture 8 times and just take inference of 8 images at a time, because the class address and literal address would remain same for a given trained model. And this is a direct encoding. You can see like the class of MNIST goes from 0 to 10, so using 4 bits. We are using the 9 bits to accommodate maximum of 512 clauses. And we're using the literal address of 11 bits because we have like 1568 literals in the MNIST dataset. This is the general overflow. That on step 1, we read the VRAM content, which has this encoded data. It reads the literal address field, the 11 bits address field, which was saying, which has the address of the included literal. And then in step 2, the ARM processor reads the corresponding literal from the off-chip DDR3 memory, which has the DDR3 has all the images, or you can say the test images we want to test. And from the literal address fetched from the VRAM, it fetches the exact literal of that corresponding to that address and writes it back to the VRAM in that space. In the last LSB, the literals, the 8 bits. And then step 3 just consists of sending some control signals to our inference custom design through the GPIO ports, on which, like, once it can start, and there are some indicators on the board which can tell you like whether the process has been completed or not. And after the inference is complete, so we can read what's the result. We read the predicted class of that. So I just go slightly through the RTL design we came along with. So this divided into 3 parts. First part was the clause computation. So this stage basically computes the clause output using the included literals only. And as I said, every clock second only one literal comes in. So the purpose of the clause computation is to like compare the addresses of the class and clause. Like first it compares the consecutive clause addresses to decide whether the incoming literal should go, to decide the incoming literal should go to which clause expression. Let's like first very small example, if there are 5 literals coming in, the first 3 belong to one clause and the second 2 belong to another. So the purpose of this computation is to compare their clause addresses and then send them to the right clause expression location. And depending on this class and clause address, the partial product is included in the current clause product or a new clause product. What I said, like whether the literal should go to a existing clause expression or it should go to another new clause expression. And once the clause output is ready, we can send it to the next stage to start, and while parallelly starting a new clause product in this stage. So the next stage is just like the summation stage. Once you like have a clause expression and you have the literals also ANDed properly, you already have the clause output at that point. So depending on the clause output and the clause polarity, we can decide like whether it should get added to the like the positive polarity or to negative polarity. And then like as per the summation algorithm, like we just add all the positive votes and add all the negatives separately and subtract them to get the class sum. And this class sum also like it's detected like at the end of a class. Like basically when the class is changing, we should update like this register gets updated with the class sum value. So in short, this stage just adds up the final clause outputs and then sends it to the next stage, which is the argmax operation. So like this basically this basically now compares the current class sum with the previous class sum. The registers like to store the previous class sum, and the predicted class register basically stores the class which has the highest class sum till then. So by the end of the process, by the end of when the last BRAM words are read, the predicted class should have the class which has the which got the highest votes from the inference. Excuse me. Now coming to the result section, there are some interesting results here. So you can see like the standard sequential design which we made, we compared it with the resource utilization with the include only sequential design we are proposing. So in terms of resources, like these are the number of units like LUTs units, register units and all. So you can see our design comes up with the higher LUT count, but that is just to like for bringing up that comparison mechanism which I showed. I will just show it again. In this one, like the comparison mechanism for the class register and the clause registers, which basically identifies whether the given literal incoming literal belongs to which class and clause. It basically does the job of pinpointing the included literals. So that's where the extra resources in terms of LUTs and all go to compare and just send them to proper place. But yeah, like the gain that we gain in terms of memory uses and inference speed like compensates for this overhead in the LUTs. So like table 2 will put the memory requirements, like how it affects the memory. So you can see like for varying number of clauses with given standard parameters like 7.5 T, 20 and 20 epochs. Assuming that one bit in one literal occupies the space of one bit in the memory, like these were the numbers we came that required. These are numbers we came that the memory required for inference, like basically storing all the literals. So as you can see, for a number of clauses, like for 500 clauses, our proposed design needs like 499 kilobytes of memory, while the around the same is required in for 250 clauses in the standard design. So as you can see, as you can increase the number of clauses in the TM model, the total memory increases as more TA states are introduced, and number of TA states are actually equal to the number of literals are involved in a standard inference mechanism. So standard inference design like scales up largely due to this fact, as each clause would require as many TA states as there are literals. But include only architecture stores only the included literals in its memory, like those literals are only included, and hence the memory requirements decreases drastically. This was one of the thing we came along. We could save a lot of memory by only storing the included literals with a few overhead for the addressing mechanism. Now, one of the things that helped to really helped to leverage this mechanism was the literal budgeting, because we are trying to leverage the less number of included literals, and literal budgeting really helps down to cut the requirement even more. So you can see in the table as itself, let's go for the first row, like for 500 clauses, S and T at the values. Without literal budgeting, we are getting an accuracy of 97.21, and this number of cycles is basically you can say the number of literals you had to give input. So because for every literal we take one cycle, but with literal budgeting, the accuracy was slightly compromised to 96.38%, but the number of cycles required for the same were decreased by a very large margin, because with literal budgeting, even each clause just have to make their clause expression with 12 or 18, a number specified by us. So it had only to form its clause expression with 18 literals. Anything more that comes, it had to drop some other literal. That's how the literal budgeting work, and it helped a lot to decrease the number of includes, even decrease the number of includes, and even we could come up with very small number of cycles to gain almost the same accuracy in terms of number of clauses, S and T parameters. So, and we're expecting it to give better results on bigger data sets, because the more we scale the number of clauses, the more number of features or more number of subpatterns we can identify, and without increasing the number of literals much in the process. So yeah, in this process, we could come up with some faster and more efficient inference algorithm by using only the included literals. Then we could design and run an hardware accelerator for the same on the Z board, Zinc 7000 Z board. Then as you could see, we saved a lot of clock cycles compared to a standard inference mechanism, and also a lot of memory space on hardware using our design. So this inference design is sequential, so it is scalable to larger data sets also, and it's memory efficient and fast to summarize it at once. These are some of the major references. Yeah, I would like to thank my professor, Mr. Srinivas Boppu, research sir, and along with DAY1 and Siddharth, who helped me a lot in getting all the things sorted for this. Yeah, that's all from my side. Thank you.
Thank you very much. Right, so there are some questions. Yes, one question. Yeah. Okay. And we are back to our schedule. Any questions? Right, Prajwal, I do have a question. So my question is that, so your design mostly, I'm not sure whether you can hear me well. So your design mostly is to improve the hardware side, right? So what is the balance between the hardware and the accuracy?
I'm sorry, could you repeat it?
So your design is mostly to improve the hardware design, right? So we reduce memory, we reduce number of, we reduce hardware. But what about the balance between hardware and accuracy?
As I said, I just showed in the results also, the accuracy is slightly compromised, as you said, if we had to reduce our resources and clock cycle, 97% accuracy on the software might give you around 96.4% accuracy on this hardware. But yeah, it speeds up the process very generally, very fast. If the same thing has to be had done in a standard method, it might have let's say taken n units of time, but doing that on this include only inference architecture, it takes about let's say n by 10 times. So
right. Thank you. So from my experience, if you train for longer, you can get high accuracy, and then if you save time, we can get high accuracy as well. Yeah.
Another factor is if you train this total architecture depends that we already have the trained model. So yes, if you train like you train it very long or very large number of clauses and everything for a very long, very high number of epochs. So like there's a chance that like on the hardware, that this 0.6% gap which is coming, that may reduce down to like 0.3 or 0.2 or very long, like heavy training on the software side.
Right. So thank you very much. Yeah. Thank you very much, Prajwal. So thanks a lot.
Thank you. Thank you.